Great. Okay, welcome everyone. So today we're going to do a presentation on some of the work that Nick has been doing, and specifically it will be on the quantum framework. So this is quite exciting stuff, and I'm very looking forward to what Nick has to show to us today. So we're joined by Carlos, and yeah, Nick, if you want to take it away, we'll ask questions as you go through it.
Yeah, sure, please ask questions. Because it's gonna be less of a presentation, more me blabbering around about what I'm currently doing, researching and developing for our quantum framework, and just other and basically what I'm trying to study. So let me share the screen.
Okay, great.
Example. Maybe we can start like instead of starting from a quantum framework and whatever this thing can do. I have this like thing I'm starting writing about something about quantum theory and how it can be interpreted in phase space and classical approach to probability theory. And I have like this small chapter about classical negativity and probability. Is it still shared?
Yeah. Yeah. Okay. Yeah, let's go through this. Can you zoom in like maybe one notch more?
Yeah, we can make it bigger.
There we go.
So it's like I wrote this small chapter, like some kind of introduction or motivation for how like quantum theory and its weirdness with negative probabilities and things like that arise even classical probability theory. So it's like a motivation we can easily go through. It's very elementary, starting with some simple coins, right? And probability theory of just coins and how it can arise with how it can lead to negative probabilities, and then some cool geometry and how we've been working on some within this thing with these things in quantum framework and how some of the things been developing. Okay, so I guess we should start like just like reminding everyone how coins look like and how they work, right? So if you have a coin, heads or tails on, in this case, like red, blue, green, red sides of the coin, so the coin can land either green side or red side up. The coins can be biased in a way, right? Usually we used to a fair coin so that it has 50 probabilities of landing on either side, right? But it can be biased, even completely biased, so that it 100% of the times landing on a single side, right? So it's a and all the space of those kind of coins can be represented by a single line, which is by one number. So it's a one-dimensional space, right? Usually called a simplex for this particular two-dimensional binary random variable is just a line, right? So any potential biased coin is just a point on this one-dimensional simplex, and those boundaries are those deterministic cases when it's just 100% deterministic coin that always lands on the single side, right? And any arbitrary coin, biased or fair, right in the middle, the fair one that lands with 50% probability is right in the middle of it. Some biased coin that maybe has some tendency of landing green more often than red, in this case twice as often, right? It's somewhere not in the middle, but towards the green one, right? So that's how you can represent any kind of coin just as a point on the space. And now you can ask yourself, like, okay, what would be, why would we pick this kind of basis, which is like as a binary, as is the boundary of this particular simplex, right? This line. In theory, we can like throw all technical like advancements of linear algebra this problem, right? So that we can just pick any basis. If we can represent any point, any coin on this line using two coordinates, right? We can pick any basis, linearly independent vectors or points, so that we can represent any point in this space, right? So we can pick like this blue one or yellow one, which has some decomposition through this basis, but it is like some other basis that we can choose and measure or represent any other coin using that particular basis. And so like there's some kind of calculation in the Wolfram language, like how we can do that and determine that every coin like in between can be also represented as some kind of convex map of those bases to that so that it's also the coefficient's going to be also be can be represented as probability. So it's like positive numbers between 0 and 1 that sum up to 1, right? But it's like non-surprising that if you pick a coin outside of this boundary that you chose as a basis, if you decompose this this point coordinates into this basis, its coordinates no longer be valid probability distribution or valid probability numbers, right? It's going to contain some values outside of this 0, 1 region. So some of the probability can be negative, some probabilities can be greater than 1. So okay, and we did nothing quantum, so it's just like pure classical approach. How could you derive some negative probabilities just by using some linear algebra of probability? So the question is, why would negative probabilities be solely be the domain of quantum theory? Because it's not really weird in this way. It's just like a side effect of applying linear algebra to your probability vectors, right? So, and you can be even weirder like that. You can be even more weird. You can pick like not just your basis as some real coins that can be actual points on the simplex. You can choose any points on the space, right? Because like linear algebra is like this two-dimensional space. You can pick like basis, even pick your basis as like of two non-real coins and decompose your real coins using those bases, right? And this would be completely nonsensical. And that's basically what I claim is what actually happens when you do quantum theory in phase space.
So
right?
it's like an imaginary coin?
Yeah, it's like an imaginary coin in a way that you just use as your representation of representing your other coins that are real. You're just using some math tools essentially to represent those. And that's basically the same as when you do the quantum theory using complex numbers and Hilbert spaces, right? You're just using some math like of imaginary numbers and unitary transformations, right? But it's not the only math that one can use in order to represent quantum processes. So that's basically the classical motivation to phase spaces. I have some generalities, like nice geometrical intuition about those things.
Can I ask, Nick? Can I ask something here?
Yeah. Sure. Please.
You might go into this now, but if I understand correctly, the space of coins, right? Like each coin, you're equating with a probability distribution that you would get if you would throw it like an indefinite number of times, right? Like all the outcomes that will come out of indefinite number of times. So I wonder, like obviously, the counting of outcomes, right? That is
frequencies.
Yeah, the frequencies, right? Those are the things that classically we sort of constrain to be positive, because how in the world are you going to get -3 counts just by counting something, right? Or or two halves, or two halves is one. Sorry, but 3 halves or something. You wouldn't be able to get those as counts in an empirical setup, right? So how do you what is the translation there? What is the sleight of hand that is but with the real coins, the non-real coins I understand, but with the real coins that you say you take some that are biased, how do you?
That's the sleight of hand that I just did. It's just a little bit of linear algebra magic, right? So it's like the whole sleight of hand is encoded in this. Yes, sure, you can represent and encode any real coin as in any of those competing interpretations, like frequentist interpretation versus Bayesian one, for example, right? When you have interpretation of probabilities as some frequencies of events or some beliefs of some party or an observer about this system or coin, or you actually can represent it by a physical coin that is biased, right? But just the actual experiment of it throwing this coin many times and counting the different events, different outcomes, without actually measuring or implementing this experiment. You're kind of already representing this instance of an experiment as just the real coin itself, right?
So is it fair to say that the negative numbers that you get here are essentially sort of the arithmetic compensation of, say, when a coin gives you too many of one result, and you say, well, actually, take those many and subtract this much so that you get the correct amount that you want, right? Is that more or less the intuition that you should have here?
In a way, it's like if you have a bias, right? If you have a bias of coins that you like, if we pick the actual bias that are real coins, you can measure any coin in terms of it, right?
Yeah.
Kind of by some experiment, especially when it's in between. Like if you have like the coin that is outside and it has this negative coefficients, you can no longer like measure it using like some consecutive like throwing of coins. You have to do some inference actually, right? That's when you have to do this process in reverse and determine what distribution caused this, given this stochastic process, like something like that. You basically will do something like Bayesian inference, which is the tool that you use in order to reverse your conditional probabilities. So
Right.
you can, but when your coins are completely like outside of the simplex and themselves doesn't represent any real probabilities, then then you can treat them completely imaginary things, that just some artifact of the linear algebra.
Right, sure. But I was interested in the case that I could imagine them being biased, because intuitively, I mean, for my understanding, I guess the audience understanding is that you might have a coin that is biased and is giving you more results of a kind that you want. But in practice, empirically, you can only count, right? Like in an experimental setting. But the idea is that you might need to subtract at some point to compensate for the difference of frequencies, right? I imagine.
Would that not be something like throwing an imaginary coin that has the opposite effect, and then just adding those two counts together? So in other words,
I don't know. We can speculate at what that actually means to like throw an imaginary coin. I'm just saying that there is like some you have this distinctness of real things and imaginary things even in classical probabilities.
For sure. Yeah.
So it's like you can describe things that are imaginary in terms of these coins, but purely these transformations, and you can distinguish what is real and not what can be measurable by such means.
Yeah, that's none of it. That's a very good point for sure.
Yeah.
So is that a quasi probability? I just saw the word there in your notebook.
Yeah. So those things that are usually not considered conventional probabilities, numbers between 0 and 1s, are called quasi. Sometimes it's not. There's some other restrictions, even when they're even positive, are called quasi, but maybe later. I'll explain when this happens. Okay, the next, what I was going to show, like generalizing this a little bit higher, go into higher dimension and drawing some cool geometries, how it looks like. So the one dimensional is just simple line. You can increase one dimension. Now you have the simplex embedded in 3 dimensions, which now is a triangle. Now every point on that triangle is a 3 length vector. So the probability vector has a size of 3. And now again, all the probabilities sum up to 1, right? And you can even increase the dimensionality. Like there is like a very convenient region function that kind of generalized to arbitrary dimensions. So, and simplex, given some identity matrix, those are going to be like unit vectors, because identity matrix consists of unit vectors on all of your 4 axes or 5 axes. Those would be the vertices of that simplex, right? So in case like if you have 4 points now you have a 3-dimensional simplex, which is a tetrahedron, I guess I can even show it now here, like that, right? So a tetrahedron is a 3-dimensional, but a simplex itself is embedded in 4 dimensions, right? So now, and you can go up the dimension like that and represent all the simplexes and even sample some points. And then again, each random point on any of the simplex and any of these finite integer dimensions would be a probability vector with positive probabilities that sum up to 1, right? And because of this nice position of the simplex, right? You know that it's 1 dimension less that it's embedding space, right? You can kind of project it down 1 dimension so that you can show it even in this case when you have a 3-dimensional tetrahedron embedded in 4 dimension by doing this rotation, right? So for example, this kind of natural rotation of the simplex that you can do, like in 1-dimensional simplex, you can rotate basically 45 degrees so that align it to any axis, either to x-axis to y-axis, and then basically take this axis as your actual probability, right? In case of 3 dimensions, you can also rotate it by 45 degrees and put it side by side. And there's like a very convenient function that you can even use. It's called a ternary plot, right? You just basically give it a list of points, and you can represent any 3-dimensional probability vectors this way. It's like a projection of that 2-dimensional simplex in 3D, right? And if you rotate the same way your 3-dimensional simplex that was embedded in 4D, you get a tetrahedron, right? By the same rotation. And if you're curious, I was just performing the literal rotation of this vertices of the simplex in 4 dimensions. I was even playing with even 1 dimension higher. Now now you can show it as a movie. So it's a tetrahedron living in 5 dimensions, 4-dimensional tetrahedron, 4-dimensional simplex. There's like a different version of it. It's like pretty hard to actually derive the equations of the simplex, so I haven't been able to do that. So it's just some numerical approximation of it.
What's the difference between the first one and the second one here?
This one and this?
Yeah.
Those are just different methods of visualizing. It's just a little bit chunky looking. It's just some numerical errors depending how you actually derive the points on each one on this simplex.
Okay, so basically one of the dimensions here is time in order to make it move. Yeah. Very cool.
If you would show like this 3-dimensional simplex embedded in 4D, you can also take one of the dimensions as time, but then you only see this tetrahedron on a single frame, right? So basically it just exists. It's like in this case, it was just if you slide in a plane and if you only hit the triangle once, right? You'll see it and then immediately it's gonna disappear. And similar for lines, it's gonna be the same picture. Right, so this is basically the geometry of probabilities, of discrete finite probabilities, right? And now we can, I guess, jump to the quantum case and just motivate how, just purely geometrically, how would actually just, as an assumption now, as an assumption now we can just assume or just like how the geometry of the quantum space looks. Right? We already know for a qubit it's very easy, right? We already know the famous block geometry, so that each quantum state, we don't know what the quantum state is. Just I claim that it's gonna correspond to some probability vector, but I know the geometry of the quantum states, right? From classical quantum information theory, and I know that it's this Bloch ball, so you can represent any quantum state, including pure state or mixed state, by some arrow in 3 dimension, and this arrow always going to be inside this ball. Right? So here I'm already using the quantum framework. So it's like you can generate a random mixed state and show the Bloch plot for that state. Mixed states are always going to be inside the ball. The pure states are going to be on the surface. So it's on the surface on the surface of it, right? So that's the difference. So that's kind of a geometry of the quantum states. And just comparing those, that we know that how the actual probability space geometry looks like and how the quantum state geometry looks like, kind of seems natural to embed one into another. If we're willing to represent all of our quantum states as probability vectors, so it would be natural to just try to just put that ball inside of the simplex, right? Or like inscribe it inside of the tetrahedron in this case.
So is this 3-dimensional by default when you generate that quantum state?
Yeah, by default it's a qubit, right? A qubit is 2-dimensional in the conventional Hilbert space representation, because you can, like as a vector, it's 2 complex numbers or a 2x2 density matrix. Hilbert, like Hermitian, positive, semi-definite, and all that. But the geometry is 3D, so you can still represent, because 2x2 density matrix, right? So if you take arbitrary random mixed state and ask for its density matrix, it's going to be 2x2 Hermitian, and Hermitian matrices, 2x2 Hermitian matrices, they have 3 degrees of freedom. So basically that's how you can also think about it. Because the 3 degrees of freedom can be also mapped to 3-dimensional vector. Right?
Got it. Okay.
All right. So as I said, that every qubit state can be represented as a three-dimensional block vector, and it would be natural to just embed this quantum space into probability space just by inscribing with this probability simplex above, right? This one is like a projection from 4 dimensions, because as I showed that tetrahedron for the you get the tetrahedron one when you project down your 3-dimensional simplex from 4D, right? By doing some kind of rotation, right? So in this way you can see that this is a projection, and you can also imagine that actually the block sphere, the block sphere and the quantum states are also, and the block vector is also actually should be 4-dimensional, and it's a projection from 4-dimensional probability space. Now we can and this is like how would some square root dimensional quantum states look like if you just continue this analogy, right? So in the 2-dimensional or 1-dimensional simplex, it's going to be your simplex kind of going to be equal to the quantum space, because it's a 1-dimensional circle is still going to be aligned. There's no way of embedding them, right, without stretching, so they are equal. So there's no quantum probability theory that is interesting for this kind of simplex, right? But in this one, it's kind of interesting because now you have a circle, or a disk rather, embedded in this triangle that can be representative of some quantum states, but it's going to be in the conventional dimensionality representation is going to be a square root of 3-dimensional quantum state, something like below qubit, right? If your qubit is 2-dimensional, now we have a square root of 3-dimensional quantum state, which is going to be the states of which are going to live in this 2-dimensional disk inside of 3-dimensional, this 2-dimensional simplex, which is a triangle, right? So it's kind of fun to play around what would this quantum theory look like, right? It's not gonna, we're not gonna do it there, but it's kind of also fun. I even come up with this name, the name for it. I call it Scootrit, right? Because it's a square root of 3-dimensional qubit, kind of square root. So it's nice, Scootrit. Yeah, like
That's
this.
cute.
Yeah, so it's a fun name. All right. So what else? So and now I'm
Can I
ask, show
Nick, can I ask something?
Yeah.
So I want to make sure I understand. So that's meant to be the phase space of possible probability distributions, right?
Which is just the simplex itself?
Well,
Or the disk?
both, I guess, right? So the disk is a subset of.
Yeah.
Okay, so
Disk is a set. Yeah.
right. So that's somehow. I mean, I need to wrap my head around.
Can we use an example? So what would a point on that space represent?
No, well, Picani, like, he actually has shown some points.
Yeah.
Right. So a point, because it's inside of disk in this case, right? It represents both a probability vector and the quantum states, right? So, in other words, you can say that every point that lies inside the disk or on its boundary is a valid quantum state, right? But every other point that is on a simplex is a valid probability vector, but not a valid quantum state. But there's still some kind of diffeomorphism between them. You can deform, if you like, your disk to a triangle.
Mm-hmm.
So it's still one-to-one correspondence you can make.
Definitely.
But it's not going to be linear, but
Yeah.
it's a non-linear transformation.
Okay, so inside the circle, and anywhere inside or on the boundary of that disk, inside the triangle is a valid quantum state.
Yeah.
Okay.
But should I read much into the fact that the quantum states are a subset of classical probability distributions there?
Exactly, yeah. So you can represent, basically, if you map, that's what I'm going to do later with the phase space. Basically, I'm saying that point in the phase space, which is a probability distribution, you can represent any quantum state with a probability vector, but not other way around. You can't represent any probability vector as a quantum state.
Okay, right. Okay.
And by the way, this space is also called like cuplix, right?
Mm-hmm.
So it's like a quantum simplex, which is like subset of the simplex.
Okay.
And it's still actually mathematically an unsolved problem to determine it for every dimension or prove it's like so that it exists in any dimension. There's like a very good evidence that it actually exists, and there's a numerical derivation of particular basis that you should choose in order to derive it for up to like something like 150 dimensions and some random one beyond that. But it's still like a unsolved problem whether this complex exists in any dimension.
Okay.
It's not proven. It's not proven, but it's probably is.
Maybe not doing it now will be breaking the flow, but it'll be interesting to see the mathematical formulation of the problem, just as a. I mean, for those of us who can get the full maths, but I mean, maybe later we can come.
Oh, what kind of math? I have this notebook. Hold on, open.
Yeah. Well, just what is the open problem? I would love. I mean, I love.
Here I actually like some notebook called Kuplex, and there's like a paper.
All right.
About them.
Maybe we can share that
there-
paper.
Yeah,
Okay, interesting.
I can send you a link. Hold on. Chat. Just Discord chat. Okay. Right. So that's the paper that was introduced Kuplex. And well, it's not it wasn't introduced. Just it's one of the nice descriptions of it.
Mm-hmm.
Right, and I was kind of going through it recently here, right? Just exploring what you can do, how you can mathematically derive all the notions in that paper. Oh, that's my. Well, anyway. So I can show like mathematically.
Yeah.
Mathematically, there's like some. Maybe I should explain at least this assumption 0. That's basically what one of those tenets of cubism, quantum Bayesianism, right? They call it the I don't sure whether I can pronounce it in German. Uglikum, right? So I think it's like a primal equation, right? It's not. It's like master equation, primal equation. Well, I guess master equation already exists in quantum theory, so it's called primal equation. And the primal equation basically describes how states, probability vectors evolve after one measurement outcomes to other measurement outcomes, right? They call it like if you have some kind of quantum state in the sky as a probability and some other measurement device in the lab on the ground, and how basically they correspond to each other, right? And here it's how it looks like in the quantum framework. Here it's like I'm generating a random pure state, a qubit, which is because it's two-dimensional random pure state. Have this function called quantum phase transform. You can specify some kind of phase by basis that has d squared. It's a d squared dimensional basis. So now that's how you can convert quantum state to a probability vector. So now it's still gonna be a quantum state, but it's gonna be like in phase space picture, and its amplitudes, instead of being your usual complex amplitudes for the conventional quantum state, it's going to be probabilities in the phase space, right? And tetrahedron basis is just a name of the basis, now one of the nicest bases for qubits, right? Because the actual basis elements are the points on the tetrahedron. And I did it like that. I think I can, and they align with the. Let's see whether I can do it live. Okay, so these elements. Okay, if I map quantum state over it and ask for block vector and normalize it, I think these coordinates are going to be defined. There shouldn't be any complex numbers in here. So this is like a coordinates of a tetrahedron, and I made it so that they would coincide with the built-in Wolfram language polyhedron coordinates for the tetrahedron object. So if you do this and you also normalize it, they should match. right? So that's why this basis is called tetrahedron, so that the actual basis elements are, if you make quantum states out of it and see where they map in the block sphere, they're gonna be a points of polyhedron, tetrahedron in this case, right? So next, what this primal equation is saying, that if you also transform arbitrary operator, even a measurement or unitary one, you get some kind of matrix in this basis, right? Like don't bother how you actually derived it with some discarding everything, right? So and then the master equation would just simply look like, think like this. Basically, your measurement probabilities would be mapping, right? And would be the same as our probabilities of our quantum state in the usual computational basis or spin up, spin down basis. Depends how you would interpret it. So that's like we basically derived or circumvented all this Born rule and measurement problem. We just purely defined how you derive probabilities in the ground in your lab, right? For the spin up, spin down measurement by purely some probability in the sky, right? Of those like 4 bases that represents vertices of a tetrahedron, some kind of outcomes, special basis, how they map to those 2 outcomes that we actually measure, right? And this matrix, by the way, it's like in this case it's like 2 by 4. It's not square, but it's still a stochastic matrix. Means that it's, if you sum up the columns, you get all the ones. So it's like it acts as a conditional probability table. It's basically, if you have this measurement, I don't know, like device that you unobservable with 4 potential outcomes, right? If you pick one of the outcomes, just look up this conditional probability table. So it will tell you how to pick up one of those 2 probability outcomes that we actually measure in the ground, on the ground, right? The only problem here is that there's also some negative values in the matrix itself, and the way you circumvent those kind of negativities, right? You can do it with the help of some Bayesian inference, for example. And I guess I can show it in detail if you want, right? So
yeah, before we go into that, I just wanted to pick up on that analogy you used, and I wanted to ask a question if it might be accurate to say that when you flip the coin, there's a moment when the coin is spinning in the air and it hasn't yet landed. Could you say that this is a capture of that state, of the state of the coin spinning in the air and not yet having landed? Like would this like encapsulate the data of that like moment in real life?
Yeah, but you don't have to like have this particular moment captured. Just coin lying on the ground, not moving. It's already representative of that. You know, it's like I have this analogy. If you have a hard drive with all those software and games written on it, lying without not connected to a computer, it still has all of this potential data that can simulate like some potential complicated worlds, right? It's still there. It doesn't have to actually be like in action, dynamically moving. So it's just so the physics project actually has some nice analogies as like an initial state, right? It encodes the whole evolution given you know the rules, right? So they causally inferred, and you can encode it. It's like a point in the roulette or whatever, right? So you represent the whole evolution by just the initial state and the set of rules that you can do run for making your evolution run in a way.
So the set of rules there would maybe be something like the specific speed of the spin, or like maybe the technique of how you've actually implemented the causality to start unfolding within that quantum space, something like that.
Yeah, you can imagine different like actual dynamical systems that simulate the same probabilities, right? You can imagine, if you want to talk Wolfram physics project, you can imagine if your probability vectors instantiated and is interpreted as some kind of concentrations of stuff, this frequentist. So if you want to employ frequentist interpretation of probabilities, you want to find what kind of concentrations or what things it describes, right? So you can imagine that you have some giant hypergraph and a single hyperedge, and there is a multi-hypergraph. You have multiple hyperedges between particular set of vertices. You can just count it, and that describes some kind of concentration of one thing. Or maybe there's a different hyperedge. This is like concentration of another thing, and you just count them up, and that would be representative of some kind of probability distribution. And just applying some rewriting rules on that hypergraph would change hypergraphs and change those concentrations. But at the end, you still have normal probability distribution of those things evolving in time. So
Okay, that makes sense.
yeah, it's just the quantum theory basically employs some has this some kind of constraint on what probability distributions are allowed. Well, I guess our conventional quantum theory makes that, because you can maybe speculate at what maybe there's actually all kind of probability distributions for those outcomes that are even located in the vertices of that simplex, those, right? Even though they're not quantum states conventionally, but maybe they somehow this nonlinear transformational mapping to the actual qplex happens somewhere anyway. Right?
Makes sense. So you're saying that there's a way to use Bayesian inference to remove the negative numbers here.
Yeah. Actually, I actually shown this here. Like here, given this matrix M, which corresponds to a measurement, right? Which you just multiply on your input probability vector, get the output probability vector. You can do this kind of somewhat simple decomposition. You basically subtract the minimum value, and that minimum value exactly would be the most negative one, right? So you can shift it by this most negative value, so that now the most negative one just becomes 0, right? Rescale it, and you kind of get this new matrix. And it turns out by this shifting and rescaling, this R matrix now always going to be a normal stochastic one. It's like, again, column is going to sum up to 1, so you still can think of it as just a conditional probability table. But now its values are going to be positive because you shift it, right? And then the leftover part is just some other matrix 2 by 2, I think I called it. Basically now you can decompose this scripted term by this R, which is normal stochastic conditional probability table, and this capital M1, which now is just 2 by 2, or again, quasi-stochastic matrix, but in a special way, in a very simple representation. And the simple representation because its inverse, even though it's itself quasi-stochastic, its inverse is not, right? So in a way, you can think of this part of the evolution, there's like a two-step process happening. Instead of there's just one quasi-stochastic process, you can't interpret probabilistically directly. You imagine it of there being two processes that happen in sequence. You just do some stochastic process by resampling your outcomes, for example, and then there is a process which inverses a stochastic, so which is just another way of saying there is some inference happens, right? So now you have to apply the Bayesian inference to infer that what the probability, like you can also write this as M inverse, right? Now it's like both left-hand side and right-hand side are just normal probability vector evolutions with stochastic matrices. So just purely can be interpreted, both sides can be interpreted purely probabilistically, but they run in different directions. So this kind of interpretation has some connections to even those other interpretations of quantum theory, like transactional interpretation, when they, they imagine that there's some kind of transaction back and forth, going forward and backward in time, or some like those advanced and retarded wave interfering with each other, those kind of interpretations of quantum theory. That's basically another way of saying that this backwards process is akin to Bayesian inference because of this reinterpretation of a usual quantum process that has some negative values in it.
Okay, I have one quick question there. So if we look at the matrix where it had a -1. So there was a 2 -1 and then 0 0 0 1 1.
Yeah.
So these are all like, can you say that the difference here when you use the Bayesian inference to convert them to only positive is that now they are not whole numbers, and that now you've implemented like fractions? And are there any
So the
trade-offs to that?
probabilities here, the not whole numbers here, just by accident for this particular measurement that I chose. It just has this very nice simple form in the basis we chose, the tetrahedron one. They doesn't have to be whole numbers. They can be square
Okay.
roots there and all that. The only condition is that the columns sum up to 1. That's the quasi-stochastic part, roll stochastic part. And you can map to decompose it into just stochastic and inverse stochastic, right? So this forward and backward, in probability theory even, there's a notion of Kolmogorov forward and backward equations. So that's the connection, just this kind of processes. And
Okay, got it.
yeah, there's a nice geometric way of thinking about those matrices. Even like this one I showed for the measurement, it's kind of a bit ugly in a way that it's not square because it reduces the dimension because you're doing from this 4 outcome probability vector to two outcome vector. But if you do the same kind of thing for the unitary, something like take random quantum operator, not one, in random unitary operator, you don't have to discard anything anymore. In the same basis, you again get some quasi-stochastic matrix, right? Meaning that it's a row is gonna sum up to sum up to 1, but it's not just quasi-stochastic; it's actually doubly stochastic. It means that just columns also sum up to 1. So that's the nature of reversibility of unitary operations, right? You can think of it as just either in both directions as a stochastic process, and you can decompose it in exactly a similar way as a purely stochastic one and some inverse stochastic, so that it's again this forward and backward things that's happening when this process is being applied. And you can do it for any kind of quantum process, no matter like either it's a unitary measurement or any quantum channel in general. You can think of it this way, that there's like, I have like a picture of this, let's try to find one. Have this hypergraph picture of this forward and backward process. Let me try to find it. Close.
While you're searching for that, maybe I'll ask Carlos a question about this. Is this quite like a bold claim to say that you can explain quantum states as just probabilities, or is this kind of like quite a simple like thing to think about?
I mean, my understanding is that certainly you're dealing. I mean, quantum mechanics is about probabilities in the end, anyway. So, I mean, I like the classical example in the beginning because it highlights how quantum is more like a choice within the possible probability theories or in some generalized sense. So I don't have much experience with that because I haven't really worked with probability theory myself, but I have a lot of experience with the differential geometric and sort of analytical mechanics side of the question, and there's a similar story going on there. Basically, dynamical phase spaces, which are a bit different from what we're calling here phase spaces, I think, but dynamical phase spaces have this similar sort of story going on there. Basically, you have your classical mechanics are essentially you have your cotangent bundles. I mean, technically speaking, so you have a configuration manifold of positions, and then basically you take positions and velocities, and that constitutes the space where your dynamical equations are defined. And in quantum mechanics, instead you take a Hilbert space and you look at the projective space on that Hilbert space, which essentially means that you do unit sphere up to face at every point. And so what's very interesting when you look at those from a purely differential geometric point of view is that in both cases you begin with a set of configurations, something that you can know about a system somehow. In the classical case is the configuration space of positions. In the quantum case is the Hilbert space, that is basically a vector space spanned by all the possible observables or all the possible states that you can get access to. And in both cases, what you're doing, you're sort of canonically trying to find what is a symplectic manifold, or Poisson manifold that gives you a Poisson bracket for dynamics that are Hamiltonian, conservative, etc. And what is interesting in both cases is that in the classical side, you end up with a construction of the canonical Poisson structure in a configuration space, which is this thing called the cotangent bundle, which essentially means positions and momenta, positions and velocities. So that happens to be a manifold that is non-compact and has, can have non-compact directions because velocity can be arbitrary and so on. But on the quantum side, when you begin with a Hilbert space, you do a construction that is called the Fubini study construction, which is taking the Hermitian inner product of the Hilbert space and restricting it to the unit sphere and basically quotienting it by the phase transformations. And that happens to define a Poisson bracket on the projective Hilbert space. And in fact, this is the well-known result of what was it called again? Ehrenfest theorem, I think, where you can write your dynamical equation, basically Schrodinger's equation can effectively be written out as a Poisson bracket equation, just like in classical mechanics. So that's no coincidence. There's not like mysterious thing going on. It's just that mathematically you ended up with the same thing. So I gave you this very little story about the differential geometry of quantum and classical because what I am understanding about this, which I'm still sort of learning, is that there's a similar flavor of story going on. And maybe Nick, you can correct me if I'm wrong, but there's this flavor in classical and quantum dynamics that they are essentially the same kind of dynamics, but the phase space in one is very different from the other. Phase space in classical is unbounded and sort of more linear. It's a vector bundle, and in the other is a projective space, which is a compact manifold. It's like, turned into itself.
Well, I can describe how quantum, at least for the finite discrete systems, I can describe how the phase space there looks like in more detail, by example. Like this way, by the way, this is the picture for this decomposition, so that I'll just briefly review what is going on here. It's like if you have this arbitrary quantum channel or quantum circuit, right, with all the operations, unitaries, and measurement, you kind of transform.
Can we zoom in one notch just for the stream?
Right. So basically, in the circuit, you can replace, as I showed before, you can replace every unitary or measurement because it's a matrix, right? You can decompose it into two matrices, like this decomposition, which one of them is like happening in reverse, right? So you can imagine that there is actually, for every kind of process, there's some intermediate random variable happens that you have to match together so that this forward and backwards process coincide together. So that like this one is forward process and the backward process, and it's basically some kind of you get some kind of Bayesian network from every quantum circuit by this mapping. So that's like every index, every wire in the quantum circuit would represent a random variable, some finite dimensional one. So like this one usually 4-qubit, this one's going to be 4-dimensional one, but after the measurement, so you can see that the wire is getting thinner, the dimensionality is getting lower, so this is the outcome of the measurement, right? So that's what you get. And then that matrix M that we had before, instead of this hyperedges that you would have to draw if you have this 2-qubit out, 2-qubit in, 2-qubit out kind of process, you have to just a single hyperedge going in one direction. It's just because it's no longer a tensor product of two. Right? So basically what I'm saying is just quantum circuits are Bayesian networks in some way. In this way, right? So now
is that a Bayesian network on the right hand side? What you've drawn there?
In a way, yeah. It's a little bit like different because of like usually there's some a cyclic kind of thing. You have to the actual Bayesian networks are constrained to some structure to them, but there's a like more general constructions of factor graphs, right? So you can represent the whole computation of a quantum circuit. You can represent as some kind of factor graphs with random variables, and you can even downsample every random variable to just binary variables. So you can just have a network of binary variables with some connections, and you can even expand it into some kind of polynomial and do the optimization. There's like optimize it and get the same result. So it's equivalent. That's the same thing as running the Bayesian network is kind of the same as doing optimization of a Boolean optimization of those random variables with some real coefficients. So it's a pseudo Boolean optimization process. That's just another way of looking at the quantum circuit computations. And we're just looking at different interpretations. So there's many ways of thinking about quantum circuits. I was going to talk about phase space anyway, because Cowers was starting describing the classical phase spaces. I was just going to mention like what we have for like what I showed there for the tetrahedron one, right? It's a technically it's a phase space, right? But it's always it's a special phase space because then when you actually get the probability vector, there's nothing never gonna be the negative probabilities and all that. But conventionally, what people call phase space, they refer to some Wigner distribution, right? So some distribution in like position versus momentum kind of space. This two-dimensional, or not two-dimensional, but space depending on two variables conjugate to each other, right? And there is also an analogy in the finite-dimensional cases of the Wigner phase space, and it's so special that we even have like a special function that does a similar transformation. So it's like we had this raw state, and you get the new quantum state in the phase space, which is now four-dimensional, and now in general its amplitude is going to contain negative values. So that's the more famous quasi distribution of Wigner in this simple qubit case, right? And why it's so, and this Wigner transformation and this Wigner phase space is actually has some very nice properties of phase space. And why is it called phase space? Let me fetch some of the. I have some nice visualizations here. Oops. Is it waiting? Damn. What variables do you have overwritten? I know. Excellent set. Come on. What's this? Okay, let me struggle it. Let me just quit it. Try again. This one is coming.
Live preview of our Nick does troubleshooting.
Live coding struggles.
Very impressive.
Where are the posted? Yeah, attempt number 2. Maybe it's gonna work. Okay. So this is like a simple 5x5 dimensional phase space now. So it's like a qubit. It's a phase space for qubit of dimension 5, and what it shows you the actual probabilities, those quasi probabilities of the Wigner distribution, which can be positive and negative. But it also has this nice properties of displacement, so that if you apply some Pauli matrices, generalized Pauli matrices to those states, it's gonna like literally move your phase space like up and down. So you have some natural geometry of phase spaces, right? And there's like, and they look different for odd and even dimension. It kind of depends how you encode what kind of phase space you choose. And there's like a way of encoding in a similar fashion even dimensional one, and they have to split it in 4. So you still have this displacement of phase spaces by Pauli matrices. They move the whole phase space up and or down. So that's the geometry of phase space. So you kind of think of them as some kind of torus because they are cyclic. They are this 2x2. It's like this. They form this plane and they cycle, right? So you kind of can shape it as a torus. But for even dimensional case, there are 4 tori.
It's not quite a
For some
torus.
reason.
Are the
Geomet-
tori connected or no?
They depend on each other,
So
but they
I don't think they are exactly tori, geometrically. I mean, they have circular orbits, so they have S1 orbits, but I think they are. I mean, they are projective spaces, right? So they are these manifolds that. They're the CPMs, right? They're not exactly tori.
no. It's like I only describe this particular phase space transformation. It's just you can make for this particular grid for arbitrary finite dimensional qubits.
Yeah.
Right?
What I'm saying is
like this
yeah.
Bachmann map.
Yeah, what I'm saying is that I mean there are S1 symmetries, but that doesn't mean that it's a torus, right?
Because why? It's like
So I mean you could have you have S1 symmetries in a sphere, and it's not a torus, right?
well, it's kind of it's not this. I guess what we are confusing about. It's like the story is not the shape of the phase space itself. It's just how it.
Okay.
Right.
How it returns back to where it started. That's what you're saying.
Yeah, you can. Yeah, you just basically what I'm saying. There's some displacement operators that you can apply to phase space and rotate it, and it just the way it's doing that, you can rotate the phase space and it turns back on itself, right, cyclically, and you have two directions for usual continuous case that would correspond to position and momentum, right? But in the discrete case, it's like some orientation of a spin, or sometimes called spin and phase, or shift and clock. So you can either shifting something or increasing frequency.
Yeah.
And it's in both directions, right? So when you shifted the phase this way, it was cyclic, and the other way is also cyclic.
Yeah, they're cyclic in both directions. But those are just the what are cyclic and the actual quasi-probabilities.
Right. Okay. No. Okay. So yeah, because these are position and momentum variables with quotation marks, right? Like I mean,
yeah,
they are because yeah. I mean, I at some point I could, if people are interested, I could go into the details of why, like this quotation marks, because this is the conjugate variables of the symplectic structure that is underlying, but there's no position or I mean, how could momentum be cyclic, right? I mean, it doesn't make a lot of sense.
Yeah. There's no like a direct analogy immediately to continuous case.
No.
Right? It's just like it's basically only for fermionic system. There's like a mapping to the fermion ones, from qubits to fermions of our arbitrary spins.
Yeah.
But not the bosonic ones.
Yeah.
Okay. What else? I don't know if you have any questions. I can elaborate.
Are there any more pictures on the end of that notebook?
We can
The
find
first one in the background.
Oh, in that one, maybe not. Like maybe this is just a bunch of balls and tetrahedrons.
Mm-hmm.
if you want some different pictures of those phase spaces, there's a documentation for the quantum basis. Have this nice. No, again, I remembered what I wanted to show. It's like basically the connection to how they look like in more detail, to explain how they arise. Those phase spaces are represented from categorical perspective or from using diagrams, right? I just showed briefly one picture with the circuit, how it transforms to the hypergraph. But in general, if you have like arbitrary circuits, like this Bell one, for example, right? Its diagram show wire dimensions. Its wires are two-dimensional, so it's like two-dimensional Hilbert spaces, basically, living on each wire, right? But in phase space, if you just take the circuit and transform it to a phase space, like maybe again to that tetrahedron one, right? Its diagram gonna be loaded. Is it? It's thinking so hard. Okay, I don't know. So now, basically, after transforming this circuit to the phase space, all wires now are four-dimensional. So basically, now there again this grid of two positions or two momentums, if you wish, again representing each of the wires, and now each wire is also a probability vector. So it's a circuit for usual probabilistic process or probabilistic model, I guess. So now you can think like, if you, after slicing this circuit arbitrarily across wires, you can read off joint distribution for this particular thing, right? So for example, if you take operators of this circuit, oh, I know why it's so slow. Let's make it numeric, because too many square roots in there, I guess. Starts to be ugly. But basically, this operator is the Hadamard one, right? And if you can fold this list of operators one after another, applying it to some initial probability vector, you get the new probability vector after applying each of those intermediate operators, right? So any slice through quantum circuit gets you the joint probability. And if you want to represent measurement in phase space, right? If you have some quantum circuit with measurement, like maybe on the first and the second qubit, you have some measurement. Again, if you show the dimensionality of those, by default it's like not actually projecting to the two-dimensional one, but for technical reasons, because you still have to maintain the computational or the classical measurement result, so that you can measure the same qubit more than once if you want to. But if you discard those, trace them out, now your measurement doesn't produce any like separate classical outcomes. It just projects those four probability outcomes in the sky to the two probability vectors in your lab that correspond to a spin, for example. So now your dimension changes, right? And you can kind of think of it as basically that's your categorical approach, right? Now you have all this diagrammatic approach, and that works for arbitrary processes, operators, measurement, and you can even get like arbitrary channel there, right? So now there's a quantum channel that also is turned into some kind of probabilistic stochastic process on probability vectors, and it's all again is just a composition and tensor products of operators. But now they're not quantum, not living in the Hilbert space, but live in the probability space, or in the complex, I guess, more precisely. Well, so that's the pictorial picture, the pictorial representation of the phase spaces and how you represent them with diagrams.
That's pretty cool. So is this something new that's been developed, this diagrammatics quantum circuit technology?
Well, it was just a part of quantum framework from the beginning. Just the way of transforming it to phase space is not. It's kind of new, right? All those niceties of showing the dimensions. It's been just developing over the time by small iterations over this year, I guess,
Okay.
over the last year.
Okay. So basically, this package or packed is it packaged up like this if people want to play with this and do some of these examples?
I just they can do it by just simply installing the quantum framework. Usually, it's better to install it from the development link. Let me just write it down. It's gonna be this one. I have it. The short one. Development from quantum computation. Like from this link, right? And then just importing it like that. That's the lines to get started,
Very cool.
right? You can share them. So,
Mhm.
and all the examples I showed should work to do this.
Great. So are these notebooks ready to share? Can we put them up somewhere, or are we going to do like an official
Oh, if you
publishing of
clean
them?
them up, like this one, phase space is what I've been just writing. It contains this classical negativity thing. Maybe it's gonna be out some kind of short blog post, right? So we're actually elaborating a little bit more detail about all of these things we mentioned.
Sounds good.
But just a bunch of notebooks we have. Yeah, there's like I showed. There's a documentation that you can just look up. There's a. Let me show the page. So there's a page for the Wolfram quantum framework. Right. There's also an example page of a bunch of Grover algorithms like this. You can just. This is another page that contains a bunch of examples that one can explore using the quantum framework. So those pages are is a good starting point to learn about the framework itself.
Very cool. So is that's a block sphere kind of
Yeah,
image on the right?
block sphere with the circuit, and this is a tensor network.
So you're quite into block spheres, I assume.
Yeah, especially recently. Yeah,
Okay.
this particular. Well, that's not this picture. I'm not the one who designed this one, but yeah.
Yeah, it's very cool. I'd love to
Very cool stuff.
yeah, I'd love to explore some of this on our TL draw that we did last time and see how that connects to the rest of the whole hypergraph Wolfram physics project and see how we can draw some connections there as well. So maybe we can do that as another live stream.
Yeah, I guess.
Definitely.
Yeah. Very cool, Nick. Yeah,
All right.
thanks for that. Yeah, no more questions from my side unless Carlos wants to ask something. Yeah, I think that was a good stream.
Yeah, that was very, very informative. Good to be more up to date on the quantum framework front.
Yeah, there's much more to like I could have shown. Yeah, that.
Of course, of course.
Okay, we'll do that for round 2 then.
Definitely.
Yeah, maybe after you publish the blog post, then we can do a second review and cover some of the extra details after this. From where we are here, we'll cover the rest. Great.
Yeah, sure. Yeah.
Okay, thanks everyone for the live stream, and we'll post all the links to the framework, and as soon as the blog post is out, then we'll share that on our various channels as well. You can read all about quantum frameworks. Cool. And all the best. We'll chat soon.
See you soon, everyone.
Bye for now.